Mr. Johannes Kind from TU Darmstadt. Mr. Johannes Kind is a research assistant at the Institute for Technical Thermodynamics (TTD), TU Darmstadt. He completed his master's from University Bremen. Mr. Johannes Kind's research focuses on heat and mass transfer in multiphase systems, with a particular emphasis on nucleate boiling, conjugate heat transfer, and fluid dynamics in microgravity conditions, using advanced simulation techniques with open foam. Mr. Johannes Kind is also involved in the benchmark experiment Reference Multiscale Boiling Investigation (RUBI), which is led by the European Space Agency (ESA). Today, he will present on multiphase and multi-region simulations with phase change in open form.
Similar tracks. Got gas. Check it.
Hi, and welcome to the first part of my talk about this multi-region, multi-phase, and phase change with open foam. I realized I haven't put an introductory slide on open foam in my presentation, and I do this in words now, in case you don't know open foam. Open stands for open source, and it is fair to say that open foam is the major CFD simulation software which is in open source. So people like me can look deep into the code, change it. I will show some changes in the second part and widely used in academia. The first section I will pretend that we start from zero, and we have the selection of all models in the multi-phase, multi-region phase change world, and then I will detail. You've seen it all. The boiling process is the perfect example. It's multi-phase, the paper, multi-region, solid and the fluid above, and we have the phase change between liquid and paper. And the challenge is, of course, how to model. I am not in the position to give the general overview over all methods. I will rather try to give you an overview based on my PhD work in the last 4 years, which is close to this experiment which has just been presented. And I will try, as I said, try to locate the methods in out of the possibilities, and hope that you can see some universal methodologies. If you are looking for general overviews, there are excellent textbooks. There are very good reviews. Textbook example from Greta Tryggvason, who was here 2 weeks ago. And there is a company, I don't know them, but they put out high quality presentations on their website on open forum. So feel free to check them out for deeper and more comprehensive. Nuclear boiling is the best method, we know, but in gravity it's very challenging to simulate because of its rapid nature. Bubbles create flash. That's the reason why we do experiments and numerical simulations in zero or microgravity. And then there is the interplay between the experiment and me as the numerical guy. Axel said they challenge me, they challenge the numerical methods. I try to be strong, and in return, I can use the simulations as a magnifying glass and investigate phenomena which are not visible by experimental methods. And of course, I can do parametric studies without flying to the ISS. So the interplay between experimental work and numerical work is very important. Okay, let's pretend we start from zero and have to choose what kind of models to choose. And each of these three categories, they have different tasks. So multiphase needs to tell us where is the interface. We construct it so that we know the shape of our bubbles or droplets which we are simulating, and it has to affect this interface in our simulation. How does it move with the velocity or phase change? Multi-region, in our cases, we don't have large forces and no mass transfer, so multi-region reduces to conjugate heat transfer between the solid and fluid. And finally, phase change. How do we calculate evaporation in condensation? I want to stress that multiphase, multi-region phase change, we are sitting in a bigger picture, of course. We are inside CFD simulations. Above today's talk, there is choices to make, like do we use lattice Boltzmann method, or how about turbulence, even discretization schemes. And below today's level is the stuff Professor Stefan has presented. What do we do really close to the contact line? So we are in the middle of the pattern. And starting with multiphase modeling of this figure is from this review from one of the first slides. And it gives us several classification layers of multiphase methods. First one is, do we have an Eulerian interface or a Lagrangian tracking, so to say? A Lagrangian produces either really a moving mesh, which deform where the mesh is deformed with the interface, and the front tracking method introduces small massless particles. These particles are moved. They experience the force from the flow. They are moved and tell us where the interface is. In contrast, in the Eulerian approach, people introduce scalar quantities, and these scalar quantities are transported through the image. And to my knowledge, in my field of research, simulation of bubble growth, it is rather uncommon to have Lagrangian type, and many people use the Eulerian type interface. And starting with phase field method, I had a discussion with Arvind. It's very well suited for interface chemistry. It has nice surface tension implementations, but it has its problems with phase change. In contrast, the level set and the volume of fluid method, they are more used for phase change phenomena and are relatively similar. We had the talk of Professor Sharma yesterday, who showed us this level set function. The volume of fluid method is slightly different, and what he mentioned that the level set function always has the problem with mass. So you have to ensure mass is not getting lost. The volume of fluid method doesn't have that problem. I'll show why in a second. And therefore, let's state right now, let's choose the volume of fluid method for further simulation. And in particular, let's choose the geometric BOF method. And I will explain the difference between algebraic and geometric BOF. Multi-region modeling or conjugate heat transfer always is based on the Dirichlet boundary condition for temperature equality at the region where, at the patch where both regions meet, and heat flux equality. And this is the Neumann. However, if you want to implement these two conditions in your simulation, you have lots of options. Usually people use Dirichlet, the fluid, Neumann in the solid, or vice versa, or Neumann, or Robin Neumann. Really lots of different combinations. And to my knowledge, the most advanced coupling method is the Robin type of boundary condition. Therefore, we choose it, and I will explain it. And finally, phase change modeling. And there are two approaches to phase change modeling. Either we sit on the interface and look in the interface normal vector and try to calculate the temperature gradient towards the interface. From this gradient, we get the heat flux. And this heat flux, we assume, is the phase change flux crossing the interface. This method is very robust and relatively parameter-free. So it's really a good method. The other approach is assigning the interface and heat resistance. And then you only need the temperature in each interface cell, compare it to the saturation temperature, and divide it by the heat resistance to get your heat flux. This method is okay, robust, and everyone who has ever used it will know there is one factor in it which is free from 0 to 1, and it's your task to determine this factor. So based on this information, we should choose the gradient-based models because they are, for this configuration, superior. This changes the closer we get to a region boundary, closer we get to the solid. So case 1, for example, for a vapor bubble in a liquid, we are sitting on the interface looking for other values, and there are enough values for calculation. So there is an accurate calculation of the temperature gradient. The closer we get to the contact line, the less values are present for the gradient calculation. Only this hash value, and this hash value doesn't reflect how much heat is transferred in this region. And this is a problem because we've heard in this region significant share of heat transfer occurs during vapor bubble growth, boiling. And when I did developments on heat transfer, on physical conjugate heat transfer in this region, I noticed that even though I enhance the coupling properties, I bring more heat flux, nothing changes because this gradient-based model doesn't pick up how much heat is in this region. And therefore, with one crying eye, because it's not the best method, we choose the method based on the integrated method. Okay, we have chosen our methods, and I will now explain them in more detail. But first, I will show the equation equations which are used for single-phase installations. Incompressible fluid, fast, another Stokes equation for momentum, and energy, advection, and diffusion, but for just one phase. The volume of fluid method, which we have chosen, is based on the finite volume method, the upper level, and it introduces a variable called volume fraction. And this volume fraction compares how much liquid is in a cell compared to its cell volume. For example, the model is arbitrary interface, the dashed white line. The cell would have different fractions of liquid, one meaning full liquid and 0 meaning vapor. And the advantage is that all properties, all liquid and vapor properties in these interface cells are now averaged with this volume fraction, and then we can still use the one field formulation from single. And I've already said it, we need to construct the interface, which gives us the interface normal vector, very important for surface tension and contact angle modeling, and surface area, which I need to calculate from the phase change heat flux the flow, which is arising from phase change. and advection due to velocity or phase. For the reconstruction, there are two approaches. The first one is using isophases of the volume fraction. It's either common to use 0.5 as an iso value, or more advanced use variable value of this iso value. And the alternative is piecewise linear interface construction, where it's an iterative process, but so this is highly simplified. But we determine the interface vector n, and from this vector we know all possible interface alignment in our set, and then based on the alpha value based on volume fraction, we choose the correct one. And here is a comparison between the methods. Let me start with the right-hand side. This compares the error over the resolution of the mesh. And a good method has a strong convergence with finer resolution. Because the finer you go, the better it should be. And second order means it goes with the square of the cell size. And we see that iso alpha, which is the approach based on the iso phase, deviates from the straight line, and also here it doesn't even converge, which tells us this is not a very good method. And there are two other methods, both click or iso based, and they have an RBF in the back, which I will explain in a second. And we see that they are much better, and we see a small difference in the normal vector interface, normal vector, so that we state that the click RDF method is the most accurate one right now. But what is this RDF? Usually, the interface normal vector is calculated based on the gradients of the volume. Excuse me 1 second. So based on the volume fraction gradient. But with today's volume fraction methods, especially for the advection, which is coming in a second, we see we have a very sharp transition from alpha 1 to alpha 0, just one cell, which means that the gradient of this field is not so reliable. And the approach is the introduction of a sign distance function, very similar to the level set function. And this function is distributed in a much wider range around the interface. So if we take the gradient of this function, gradient calculation is much more. Coming to advection, we usually write our conservation equation of the volume fraction, this new variable, discuss temporal and advection. And as I said, or as it was displayed in the overview, we now have the choice between algebraic and geometric advection. Algebraic is we treat this equation as we do treat all other conservation equations. We discretize it, put it into a linear equation system, and try to solve. This is affordable in terms of computation expense, but happens that values outside of 1 and 0 are computed, which is wrong. And this is prone to smearing of this of the interface region. There is a workaround, a Mule's algorithm, which adds additional terms to this equation, but it remains a workaround. The alternative is geometric form. We don't need to solve this equation, but we think in geometric terms about how the interface moves. This is again iterative, it's more expensive, but it is bounded between 0 and 1. The interface remains sharp and we have a high accuracy. And the established method for the geometric volume fluid method in open form is the iso-vector method. It is 7 years old. 9 years old, sorry, but since around 5 years, it has really gained momentum in open form because it is implemented in an official solver. I won't go into too much detail, but the fundamental equation is volume fraction at a new time step is based on the old volume fraction. Then we need to calculate how much volume of liquid has been transported over each cell phase. And this volume calculation, we need the fluxes, we need the submerged area. Again, something similar to the level set presentation of Professor Shah. It's not easy. You have to read this paper if you want to really get it, but I hope you get a small insight or and for the demonstration of this higher accuracy, this is the dam rate tutorial. We've also seen this case yesterday. We have a liquid in gravity, which initially is shaped, and then we have an obstacle in the middle, and if we run the simulation, the liquid will fall and splash over this obstacle. And I hope that you can see that in the geometric Boss method, we have a much sharper interface. For example, also around here. Here we have a diffuse interface over several cells. Here we just have one interface. So this is just a graphic demonstration of the superiority of the geometric Boss method. Surface tension modeling we do with the continuum surface method. It's arguably not the best and most advanced one, but it is reliable and has been used in lots of studies. And you see now the importance of the interface normal vector because we need a gradient of it for the calculation of the curvature. So taking the gradient of a field which is inaccurate brings more error than taking the gradient of a field which is more accurate. And this is a topic not so well researched and documented. How do we model the contact angles at the wall? Some people set the interface normal vector in the contact line cell with brute force to the prescribed contact angle. Works, but who knows how physics it is. This approach from Scheutler uses those values outside of the region, and this introduces, remember this gradient in interface normal vector? If the interface does not align with the prescribed contact angle, you get a gradient in the interface normal vector, curvature, you get the surface tension force, and this pushes the interface into the right direction. But again, there's work to do, and if you're interested in numerical work, I think this is a good topic. And the final measure, we started with one equation for temperature or energy, and we split this into the liquid and the vapor temperature. This has several positive effects. We completely decouple both liquid and vapor temperature, and they may only talk to each other if we allow it. There's no unphysical heat diffusion. And therefore, we also have more control of phase change on the heat transfer, and there is a higher stability. Okay. Okay, this was with what we started, single phase, and this is multiphase. In the conservation of mass, nothing has changed. Momentum, we have introduced surface tension. We split the energy equations, and we added a new conservation equation for Boron fraction, which, as I told, is not really conservation. Well, it's not really solved in this form, but you get the picture, I hope. Coming to multi-region modeling, why do we need it at all? Well, in multi-region problems, we have a separate equation systems for our regions, so separate equation system for fluid and solid. And at the outer boundaries of these regions, we have our usual boundary conditions, printing fixed value or whatever you like. And at the coupled patch between two regions, the boundary condition has to depend on both regions. And this is what conjugate heat transfer does. Here's the equation you've seen already, temperature equality, heat flux equality. If we discretize this equation and introduce a virtual heat transfer coefficient, we end up at this relatively simple equation. So the patch temperature, the boundary condition for both regions, is somehow a weighted average between solid and fluid temperature. And the weighting is given by these virtual heat transfer coefficients. You won't be able to read it, but for reference, the algorithm now is solving the fluid region. We start with solving the fluid region. For this, we need the temperature boundary condition in contact with the solid. And therefore, we ask the solid, what's your temperature? But this temperature can only come from an old time temperature. But it's the best guess we have right now. We ask for the solid temperature, we calculate the patch temperature, and we solve the fluid. Same with the solid region, we ask the fluid, what's your temperature? We calculate the boundary condition, then we solve it. And as I said, this fluid solution is based on an old value of the solid. So it makes sense to repeat this process at least once before we begin checking for convergence in temperature between our. Now a short intro to the topic Axel has already introduced. When I started working with conjugate heat transfer and then understanding the equations behind, I noticed that this usual averaging of the properties in the interface cells at the wall, this is not correct for most of the cases, especially for my bubble growth case. Why should the vapor take part in the coupling? It doesn't touch the solid, only the liquid in contact, except for the contact line maybe, but this is another story. So this averaging of the properties, especially of the thermal conductivity, which brings down the effective thermal conductivity in these cells, is unphysical. And what we need to do is exclude the vapor from the coupling in these interface cells. And then with the Boron fraction, we have the information on how much liquid is in each interface cell. And with this information, we adapt the virtual heat transfer coefficient, which brings physicality into it, because we now really couple the solid cell with the portion of liquid which is the problem. This is an exemplary scheme. I've said it already. We only couple liquid and solid, solve it, go to the solid, couple both, solve the solid, and repeat this process until conversion. on the one hand, this introduction of the volume fraction in the denominator massively enhances the virtual heat transfer coefficient for small volume fractions. That enhancement is roughly 1 over alpha squared. But, as always in CFD and science, there is no free lunch. This massive enhancement leads to a tightened stability criterion. I will introduce this stability criterion in the second part today. Again with alpha squared. So you have to be careful. You don't get it for free. We have countermeasures against it, which work really well. I won't go into it. I just want to show the graph as I've already shown. If I use a setup very similar to this experiment where I have a heated solid and a vapor bubble, I can compare this averaging approach with the average substance and my new distinctive company. And have a look at the red and brown curve, where we see radius over time. The brown curve is standard volume of fluid method with the average property. And for this bubble growth, exploration needs 2 watts per square centimeter. The red curve is the new approach, and it just requires 1 watt per square centimeter. So in return, you can say this averaging approach needs 100% more heat flux to reach the same results as the now physical tells us how wrong this averaging is for simulations of volume. And I did lots of work on it in my PhD. I have a repository on it, and if it sounds like something you are interested in, please mail me, and you can work with it, and we can collect it. And there is a paper. Okay, what has changed for the multiphase conservation equations by multi-region introduction? We have a new conservation equation for solid. I think I didn't show it at all, sorry. And the boundary condition for this equation and for these equations are set by the new. Okay, last method, which is phase change. I want to start with stressing the phase change. We usually think about heat and mass transfer. Because we have this volume fraction value, we also have to take care of volume fraction. And you really have to do it manually. It's not like you add, for example, the heat flux to your energy equation, and then everything else happens automatically. In contrast, you have to make sure that in every equation which is concerned, the correct phase change term is implemented. Yeah? Heat fluxes in the energy equation, volume fraction, the volume fraction equation, and volumetric mass solved the mass equations. And as you can see, and as you can see here, we need the interface area, which is coming from the enhanced reconstruction algorithm. And all equations are starting with the phase change heat flux. So the question is, how is the phase change heat flux? We have decided to use the interface model. And this is based on work on Frage, Hertz, Knudsen. Therefore, I named it Hertz, Knudsen, Frage model. It's simple. Use the temperature in your cell, compare it to the separation temperature, and take care of the intensity, which is calculated by this term. And there we have this F, accommodation coefficient or incorporation coefficient. And there's still ongoing debate, work on how to determine a suitable value. Many people use zero to 5. You could try to start with this and then analyze the interesting thing is we have two energy equations. So we have two phase change heat fluxes, and they add up to the net phase change heat flux. And to me, I needed some time to really understand this very simple equation. But I hope with this figure, it's straightforward. So as soon as either the liquid or the vapor are hotter than the separation temperature, there is more evaporation. If they are exactly counteracting, which can happen because we have a subcooled liquid and a superheated vapor, we have it in the Ruby cases sometimes. And assuming the same magnitude, they can completely cancel out for the net phase. And for example, condensation, both are negative, both contribute to condensation. And in my opinion, this is a flaw of this model, because there is absolutely no information in this model about any conductivity or differences between liquid and vapor. It's always just compare temperatures over the same heat loop. Yeah, only temperatures and the same heat loop. And to me, this feels dangerous. This is a point where this gradient-based model has an advantage. So if you have problems in a bulk liquid away from the solid, I would recommend using the gradient-based model. But as most of us are using the boiling, there is work to do. In the beginning, I talked about phase change heat flux, and this application, the volume fraction equation, and the mass conservation equation. And especially in the mass conservation equation, if the phase change mass flux or flow is applied in the interface cells, we get or the numerical solver gets problems because it's the Poisson equation, the piezo loop, we usually encounter stability problems. The solution is removing the phase change terms from the interface cell and spreading them to cells which have full liquid or full vapor. This is the hard-Von-Ra model, also developed in this really helps with stability. Okay, for the final time, let's do the computation. This is the multiphase equation. We have a phase change. So a new term, mass conservation, no term in momentum. There would be recoil pressure, which is the recoil coming from evaporating vapor or from the evaporated vapor. But in our size case, it's not important. We have the two constitution energy conservation equation, the volume fraction equation. Here is the reference. It's calculation. The funny thing now is there is no official open form solver which can do multiphase, multi-region messages. We only have particular solvers which can do fast these challenges. And luckily for me, for us, there is the two-phase flow library where Henning Scholzer has brought together these modules in a high-quality open form coding. And this library has lots of knowledge from our institute. For example, the phase change models, So they are the history of how. Conclusion. I hope you have an idea of how to multiphase the phase change. They are powerful and are used a lot, but you have to know the limitation. I think that the fact that no official code, even in commercial code, to my knowledge, there is no software which can do all these things. But no one dares to make this topic official. And it's common that these codes remain scientific. But the more people work on it and bring it forward, the more chance we have for it. And I hope to let this impression open form. It's a great base. The next talk I will do a hands-on, show a little bit. Maybe you're interested. How you can really develop, dig in as deep as you want, in contrast to commercial code, to bring forward. Thank you for your attention.
In volume of fluid method, how you are going to compare volume of the liquid with volume of the cell? Which method you are using for the comparison?
I don't need a comparison if I get your question correct. It's just, it is the comparison between liquid volume and solid volume. Or could you
Like in this slide, volume of fluid basics. You said volume of the liquid will be compared with volume of the cell.
Yeah.
So how you are going to compare?
This equation.
That's
This direction?
no. Volume of fluid basics first.
Yeah, this one. So how this equation is calculated?
How the volume of the liquid will be compared with volume of the cell?
I hope to answer it in your way. It's not calculated in that sense.
It's tracking.
It's a variable alpha, like temperature, which is introduced in the system, and by reconstruction and infection, alpha is modeled and installed for.
So you start with some initial position of the interface, and from there it is advected. So wherever you have pure liquid, it is 1, or pure gas or vapor, it is 0, and then you know the exact location of the interface to start with, and then it is advected depending on the velocity and effective fluxes. So you don't need to every time check what is the volume of the liquid occupying the surge. Just the interface is only moving around based on the
It's
advection
rather
flux.
like the solver gives you the alpha, and you can calculate the liquid volume itself.
So this open form software will be extended to high pressure applications like 100 bar, 120 bar, like that.
It is capable of this. What's special in high pressure?
Like in nuclear reactor, we use around 100 bar, 120 bar for that simulation. So this open form software will be applicable there for the simulation.
What is the difficulty of oiling in high pressure?
Density difference is not that high.
Then smaller density difference is better for the solver. So I've never tested, but right now I don't see any reason why you shouldn't use it at whatever pressure you like. Try it and let me know.
Yeah, actually, I just wondering what is the exact Blick method that you are referring to in this case? You have your methods, right? The Blick, RDF.
And then
There are a lot of variants, for example. So you start with the young split, which is there in the fluent, and you have other variants. So what is?
I'm not as informed of it as you are probably. So
No,
I can only say like.
okay. Actually, the Blick that is by default is there in the fluent method right now.
Yeah, it is there. It's called geo-reconstruct.
It's a young split, and it is known not to be converging in second order.
Yeah, it's not second order, but it's definitely better than not having any reconstruction. So
No. So definitely he has. I mean, you have not implemented young split. It should be either the Elvira or there is a method called ELVIR or LVIR. So that is second order actor. I just wondering whether you have used one of those.
No, it's not my work. This presentation here. It's from the creator of the solver. In this paper, you will find the comparison. And on structured meshes, it's very close to the height function.
Height functions is one more way.
One more. Okay.
So my second question is there any reason why you used RDF specifically? The distance function,
Instead of what?
instead of height functions, let's say.
I don't have. The RDF is a new field in the solver. I don't have the height function in OpenFOAM.
You can calculate it. I mean,
It's similar to the reconstructed distance function as far as I'm informed.
probably your question is why not use a distance function and make it a CLS VOF, right? As opposed to
I'm just looking for a little more. See, RDF distance functions also, there are many flavors of distance functions. In fact, one of the first papers which came in this, there was a comparison between the Brackville's, the convolution based and the height functions and the RDF, and there Sharad comments at all. There's a paper. So she proved that actually height functions was the most superior. So it just goes from there.
Yeah.
So height function is also one.
It is, but it doesn't work on unstructured meshes.
Because now a lot of development is happening. So I think recently there are some papers which talked about height functions on unstructured grid also.
Okay.
Okay, so if not, we will stop here and thank the speaker again. We will have a tea break and then come back for a small session of demonstration. That's the final session for the afternoon.
Before we handle the session, I just want Chandra to present.
क्या बोल रहे हैं